Welcome to Physics, Current Electricity, Session 2 and 3. Aim of today's session is to introduce the concept of Ohm's law, to study about resistance and conductance, to study about resistivity and conductivity. First, let us introduce Ohm's law. If the physical condition of the conductor, that is length, temperature, mechanical strain, etc., remains same, then the current flowing through conductor is directly proportional to potential difference across its ends. So Ohm's law states that if the physical conditions of the conductor, that is length, temperature, mechanical strain, etc., remains same, then the current flowing through the conductor is directly proportional to the potential difference across its two ends. That is, I is proportional to V, or we can write V is equal to IR, where R is the proportionality constant and it is known as electrical resistance. R is the proportionality constant and is called electric resistance. Ohm's law, remember this, is not a universal law. The substances which obey Ohm's law are called ohmic substances, and which do not obey Ohm's law are called non-ohmic substances. Graph between V and I for a metallic conductor is a straight line as shown here. This is for metallic conductor. At different temperatures, V and I curves are different. As in this picture, at temperature T1 is given by curve 1, temperature T2 given by curve 2. Angle is theta 1, angle is theta 2. The slope of this line, if we are taking, let us choose a point A, drop a perpendicular. This is V, this side is I. Tan theta is equal to V by I. V by I gives us the resistance. Graph between V and I for a metallic conductor is a straight line. The slope of the graph, that is tan theta, is equal to V by I, and that is nothing but the resistance R. That means in this case we have two different temperatures T1 and T2, V and I graph drawn as 1 and 2, having theta 1 and theta 2. The slope tan theta 1 is more than tan theta 2. Therefore, resistance of the conductor 1 is more than resistance of conductor 2. That is, T1 temperature is greater than temperature T2. In the figures again, if we take it for graph conductor 1 and conductor 2, the slope tan theta 1 is greater than tan theta 2. So, resistance R1 for first conductor is greater than for conductor 2. Therefore, temperature T1 is greater than temperature T2, because as temperature increases, resistance of the conductor increases. So more is the temperature, more will be the resistance, the slope of the graph will be greater. So slope of VI graph gives the resistance. The device or substance which does not obey Ohm's law, example gases, crystalline rectifiers, thermionic valves, transistors, etc., are called non-ohmic or non-linear conductor. For these, V and I graph is not linear. So the graph may be like this as shown by the red line. So at this point we can take the slope. This is the phi, tangent drawn at the point. So if we calculate the value of tan phi, that will be nothing but dV by di. This is called dynamic resistance of that particular conductor. At that point, if we join the origin, we get an angle theta. This is called static resistance of the conductor. The device or substances which don't obey Ohm's law, example gases, crystal rectifiers, thermionic valve, transistors, etc., are known as non-ohmic or non-linear conductors. For these, VI curve is not linear or a straight line as shown here. So from this figure, this is for a crystal rectifier. The graph is non-linear. Voltage or potential difference is taken on x-axis, current is taken on y-axis. Static resistance we can write as R static. It is equal to V by I, and that will be 1 by tan theta from the figure. Dynamic resistance R dynamic is delta V by delta I, that is the slope taken at this particular point. It will be 1 by tan phi. This is called dynamic resistance. This is called static resistance. So at a point we have taken a slope. That slope delta V by delta I. This is delta V. This is delta I. So delta V by delta I will give you 1 by tan phi. Similarly, at this point we can consider this as V and I. So that is 1 by tan theta. 1 by tan theta is the static resistance. 1 by tan phi is the dynamic resistance from this non-linear, non-ohmic conductors. The graph which we have drawn here. Now we can also define Ohm's law as current density is always proportional to electric field at a point. According to Ohm's law, current density is always proportional to electric field at a point. That is, J vector is proportional to E vector, or simply we can write J is proportional to E. J can be written as sigma E. Both are parallel. The direction is same. Sigma is now called the conductivity. But we know what is J equal to? I by A. And what is E equal to? V by L. So if I substitute these values here, we can write I by A is equal to sigma times of V by L. V is the potential difference. So potential difference V can be written as L by sigma A times of I. Sigma is conductivity. We can write reciprocal of conductivity is called resistivity. So if I define rho, that rho is equal to 1 by sigma. Rho is called resistivity. So V can be written as rho L by A into I. This rho L by A, we can write it as R, or we can write V is equal to IR. This is the same old Ohm's law which we have defined. V is equal to IR, where R is called the resistance. When R is constant, V is directly proportional to I. R is equal to V by I. Only if physical conditions of conductor or wire does not change during the flow of current. R is equal to V by I, and this is resistance, units ohms. Rho is 1 by sigma, or we can write it as sigma is conductivity and rho is resistivity. Reciprocal of resistivity is called conductivity. One by one we will define, or let us define all these terms. That is conductivity, resistivity, resistance. Reciprocal of resistance is called conductance. So K is called here conductance. So we will define four terms: resistance, conductance, resistivity, conductivity, one by one. First, let us take the resistance. The property of substance, or by virtue of which it opposes the flow of current through it, is known as resistance. The property of substance, by virtue of which it opposes the flow of current through it, is known as the resistance. How to define the resistance? The property of substance by virtue of which it opposes the flow of current through it is known as resistance. For a conductor, if L is the length of conductor, capital A, let us call area of cross section of the conductor, N, number of free electrons per unit volume, tau, relaxation time, which we have studied in the last session. Then resistance R is directly proportional to length, inversely proportional to area, or R is equal to rho L by A, which is also written as M by N E square tau with respect to the relaxation time into L by A. This is the resistance R. Rho is called the resistivity of the material of conductor. So resistance will depend upon relaxation time tau, directly proportional to L, inversely proportional to area of cross section. R is also, we wrote just now by Ohm's law, V by I. So its units. SI units of resistance is ohm, the symbol ohm, and it is equal to V by, so it can be also written as volt by ampere. 1 ohm is the resistance of a conductor when 1 ampere of current flows through for a potential difference of 1 volt. So we can also write 1 ohm is equal to 1 volt by 1 ampere. It is also written as 10 to the power 8 EMU of potential divided by 10 to the power minus 1 EMU of current. This is equal to 10 to the power 9 EMU of resistance. Dimensions: volt, work done in moving the charge from infinity to that particular point. Work done per unit test charge divided by ampere. So it will be m L square t to the power minus 3 a to the power minus 2. This is the dimension of resistance. Now how we get this one? R is equal to m by n e square tau L by or 2m by. Let us look into this particular value. So what is the cause for the resistance of the conductor? Suppose we take a conductor in which the electrons are moving due to the electric fields. So as these electrons move, during the motion of this free electron within the conductor, under the influence of external electric field, they have to collide again and again either with electrons or positive ions formed by removal of free electrons from the atom. These collision causes the kinetic energy loss. The loss of kinetic energy of free electrons, hence heat is generated within the conductor. This tendency of material to hinder the smooth flow of electrons is called resistance. The property which depends on the dimensions of the conductor, we call it as called resistivity of material. Suppose due to the electric field, if we consider, what is going to happen? Due to the external electric field, capital E, the free electrons will move within the conductor. The free electrons move within the conductor. Since they experience a force, F is equal to ma, due to electric field E capital E. So the acceleration on each electron we can write as E capital E by m, where E is the charge of electron, m is the mass of electron. Due to this acceleration, the charge or the electron will acquire velocity or acquire some velocity. The velocity of the electron will be given by V is equal to U plus AT or U plus E capital E by m into T. Suppose the charged particle starts from rest and acquire a velocity in time t seconds. We know the average time taken between two collisions is called relaxation time or tau. Imagining that the charged particle has started from rest and the average time taken t is equal to tau. We can write V is equal to E capital E by m into tau. This velocity acquired by the electron or the average velocity acquired by this electron, we call it as called drift velocity. So drift velocity is the average velocity E capital E by m into tau, where tau is called the relaxation time. So as the electron move, they have to collide again and again either with electrons or positive ions formed by removal of free electrons from atom. These collisions cause loss of kinetic energy of free electron. Hence, heat is generated within the conductor. This tendency of material to hinder smooth flow of electrons is called resistance. So the electron which is moving inside the conductor, we assume it to be accelerating, so should continuously acquire velocity. But we assume that the electron inside the conductor moves with a constant or average velocity, we call it as drift velocity. So therefore, electron tend to move, or we are talking about assumed to be moving with average velocity called the drift velocity, Vd. This is equal to E capital E by m into tau. Or in terms of the potential difference across the conductor, E can be written as V by L. So we can also write E by m into L to tau. Vd is equal to E capital E by m into tau. Capital E can be written as V by L. So E by ml into tau to capital V, because we can write E is equal to V by L. Suppose we have taken a conductor like this, where due to electric field these electrons are moving. N is the number of electrons per unit volume drifting. The strength of current I is equal to dq by dt. What is the charge which is flowing? Number of electrons per unit volume. The charge of electron is E into volume, A into dl. So a small length or dl or dx we can consider. Area of cross section of the conductor is A, divided by dt. So this is number of electrons per unit volume. So into volume we have. Charge of electron is E. dl by dt is V. So NEAV, this is the velocity of electron, which we call it as called drift velocity. So it can be written as NEAVD. So strength of current I should be written as I is equal to NEAVD, where N is the number of electrons per unit volume, E is the charge of electron, A is the area of cross section, and VD is the drift velocity. So since we know the value of drift velocity, we can substitute the value of drift velocity in this relation. What is VD? Drift velocity VD is equal to E by M into L tau into the potential difference across the conductor. Let us substitute this value over here. So the strength of electric current we can write as NEA into E tau by ML times of capital V. Rearranging, N E square by M into A by L, tau is also there, tau into capital V. N E square tau by M, capital A by L into V. V is the potential difference. So we can calculate the potential difference V as M by N E square tau into L by A into I. Now by Ohm's law, V is equal to IR. V is equal to IR. Comparing with the Ohm's law relation, V is equal to IR. What we get? Value of our resistance will be equal to M by N E square tau into L by A. So resistance of a conductor is proportional to length, inversely proportional to area. This is constant. So resistance R is M by N E square tau L by A. But we know what R can be written as rho L by A. What is rho? Rho is called the resistivity. So comparing this relation, R is equal to rho L by A. What will be the resistivity? Rho equal to M by N E square tau. That means the resistivity is depending on the relaxation time, as well as resistance is depending on relaxation time. So both resistance, resistivity depends on relaxation time, which relaxation time will in turn depend upon the temperature of the material. As temperature of the material is increased, relaxation time decreases. That means the collision between the two electrons, the time taken will decrease. As relaxation time decreases, resistance and resistivity both are going to increase. Apart from this, resistance also depends upon the length of the conductor and area of cross section. So we can call resistance depending on the dimensions of the conductor, whereas resistivity is independent of dimensions of the conductor. So we can consider resistance depends on nature of conductor and its dimensions, whereas resistivity depends on only the nature of conductor and not on the dimension, that is length and area of cross section. Rho is M by N E square tau, whereas R is equal to M by N E square tau into L by A. Dependence of resistance. Resistance of a conductor depends upon the following factor. 1. Length of conductor. Resistance of conductor is directly proportional to its length. Resistance of a conductor is directly proportional to its length. R is proportional to L. Second, area of conductor, area of cross section. Resistance of a conductor is inversely proportional to its area of cross section, that is R is inversely proportional to A, inversely proportional to area of cross section. Temperature. Resistance of a conductor is directly proportional to the temperature. So resistance proportional to temperature, which we'll study in little bit more detail. Variation of resistance with temperature. Let us take if R0 is the resistance of conductor at 0 degree centigrade. Resistance of conductor at 0 degree centigrade. RT, resistance of conductor at T degree centigrade. Alpha is the temperature coefficient of resistance. Then RT is equal to R0 1 plus alpha into T. Alpha we can write alpha is equal to RT minus R0 divided by R0 into T per degree centigrade. So coefficient of resistance is the increase in resistance for 1 degree rise in temperature to that of the resistance at 0 degree centigrade. Coefficient of resistance is the increase in resistance for 1 degree centigrade rise in temperature to that of the resistance at 0 degree centigrade. If R1 and R2 are the resistances at T1 degree centigrade and T2 degree centigrade, then we can write R1 is equal to R0 1 plus alpha T1. R1 is equal to R0 1 plus alpha T1, and also R2 is equal to R0 1 plus alpha T2. Taking the ratio of R1 by R2, 1 plus alpha T1 to that of 1 plus alpha T2. R1 by R2 will be equal to 1 plus alpha T1 to that of 1 plus alpha T2. The value of alpha is different at different temperature. Temperature coefficient of resistance averaged over the temperature range between T1 and T2 degrees centigrade. So with these two cross multiplying, we can get alpha value equal to R2 minus R1 by R1 T2 minus R2 T1. So when two different temperatures are taken, we get this. Cross multiplying, you can see R1 plus R1 alpha T2 should be equal to R2 plus R2 into alpha T1. So R1 T2 minus R2 T1 times of alpha is equal to R2 minus R1. So alpha we can write it as R2 minus R1 by R1 T2 minus R2 T1 per degree centigrade. So two different resistances are given to us at two different temperatures. Coefficient of resistance we can write as increase in resistance R2 minus R1 by R1 T2 minus R2. Whereas if temperature at 0 degree centigrade resistance is R0, at T degree centigrade resistance is RT, then alpha will be RT minus R0 by R0 into T per degree centigrade. Variation of resistance of some electrical material with temperature. Suppose first I take it in the case of metals. Temperature coefficient of resistance is positive. That is, with increase in temperature, resistance also increases. Variation of resistance with temperature rise increases. Second, solid non-metal. Temperature coefficient of resistance is 0. So, variation of resistance with temperature rise is independent of this. Independent. Semiconductors. Temperature coefficient, it has negative temperature coefficient of resistance. Negative. Increase in temperature, semiconductor's resistance decreases. In case of electrolyte, temperature coefficient of resistance negative. Therefore, variation of resistance with temperature rise, it decreases. Let us take ionized gas. It's negative, decreases. If we take in the case of alloys, it is very small but positive value. It's almost constant. This is the variation of resistance of some electrical material with temperature. Factors affecting resistance. So apart from temperature, other factors in dimensions of resistance, let us consider which are going to affect the resistance of the electrical wire. First point, suppose we take a rectangular slab of dimensions A, B and C. If potential difference is applied across side A, L is equal to A, area of cross section will be B and C. So what will be the resistance in this case? Resistance R will be equal to rho into L by A, that is A by B into C. If potential difference is applied across side B, then L is equal to B and area of cross section becomes AC. So what will be the resistance? R is equal to rho L by A, that is B by AC. Similarly, if potential difference is applied across side C. L is equal to C. Area of cross section will be equal to AB. Then resistance will be R is equal to rho C by AB. Relation of resistance we know is R is equal to rho L by A, but L into A is equal to volume. So area of cross section we can write it as volume by length. So resistance we can write R is equal to rho L square by V in terms of volume. So if R is proportional to L square, if length is increased n times, resistance becomes n square times. Remember this point. Hence R proportional to L square. So if length is increased n times, resistance becomes n square times. If area is changed, L is equal to volume by area. So R is equal to rho volume by area divided by area. So rho V by A square. So here we are getting R is inversely proportional to A square. Hence, if area is increased by n times, resistance becomes 1 by n square times. Resistivity, rho. Let us discuss about resistivity. From the relation R is equal to rho L by A, if length of the conductor is 1 meter, area of cross section is 1 meter square, then resistance R will be equal to rho. That is, resistivity is numerically equal to the resistance of the conductor or a substance having unit area of cross section and unit length. So resistivity is numerically equal to the resistance of a substance having unit area of cross section and unit length. So when A is 1 meter square, L is equal to 1 meter, R is equal to rho. Rho is called resistivity. Resistivity is numerically equal to the resistance of a conductor when area of cross section of conductor is 1 meter square and its length is 1 meter. SI unit of resistivity, rho, will be RA by L, so it will be ohm meter square by meter, which we can write it as ohm meter, write as ohm into meter. Dimension ml cube t to the power minus 3 a to the power minus 2. Formula from the drift velocity we calculated, rho is equal to m by n e square tau. It is depending on the relaxation time. So resistivity is an intrinsic property of substance and is independent of shape and size of the body, that is L into A. Resistivity is the intrinsic property of the substance. It is independent of shape and size of the body, that is length and area of cross section. For different substance, the resistivity also will differ. For different substance, their resistivity is also different. That is, resistivity of silver is minimum and is equal to 1.6 10 to the power minus 8 ohm meter. Resistivity of fused quartz, it is the maximum most, 10 to the power around 16 ohm meter. So resistivity of insulator, that is the fused quartz, is maximum. Then comes resistivity of alloys, then semiconductor, then resistivity of conductor, which minimum for silver. So we can write the order like this: resistivity of insulator, that is we can call it as maximum for fused quartz, is greatest, then resistivity of alloy, then resistivity of semiconductor, then resistivity of conductors, and in that minimum for silver. Resistivity also depends on temperature, like resistance. For metals, resistivity increases with temperature. For metals, resistivity increases with temperature. Rho T, this is the resistivity at temperature T degrees centigrade. Rho naught, temperature at 0 degrees centigrade. 1 plus alpha into delta T, where alpha is called coefficient of resistivity. Resistivity increases with impurity and mechanical stress. Impurity and mechanical stress. Let us see factor affecting. In that we can study more about the temperatures. Factor affecting resistivity. Since rho is equal to m by n e square tau. So fundamentally resistivity is inversely proportional to n tau. of free electron density and average relaxation time. Resistivity is inversely proportional to product n tau, n free electron density and tau relaxation time. These two quantities are constant for a material. These values changes with temperature. When temperature increases, free electron density increases, but relaxation time fall drastically for the conductors, that is metal. Overall, n into tau value product reduces and resistivity increases. These two quantities are constant for a metal or material. These values changes with temperature. When temperature increases, free electron density increases, but relaxation time falls drastically for conductors. That is for metals if you call. N into tau value of product reduces and resistivity increases. Therefore, for metals, resistivity will increase with temperature for the metal, same as that of resistance. At 0 degree centigrade, suppose resistivity is rho naught. At T degree centigrade, resistivity is rho T. Then alpha is equal to rho T minus rho naught by rho naught into T. Alpha is called the coefficient of resistivity for two different temperatures. At T1 degree centigrade, say resistivity is rho 1. At T2 degree centigrade, resistivity is rho 2. Then alpha can be now written as rho 2 minus rho 1 by rho 1 T2 minus rho 2 T1 per degree centigrade. So coefficient of resistivity is for 0 to T degrees is rho T minus rho naught by rho naught T. For two different temperature T1 and T2, rho 2 minus rho 1 by rho 1 T2 minus rho 2 T1. For semiconductor, charge carrier density increases so rapidly with temperature that the fall in average relaxation time cannot reduce the product. Hence, resistance of semiconductor decreases as temperature increases. Alpha is negative for semiconductors. Alpha is negative for semiconductors. That is, with increase in temperature, alpha value will decrease. So, it has negative temperature coefficient of resistivity. Next, conductivity. Reciprocal of resistivity is called conductivity. Reciprocal of resistivity is called conductivity. It's given by sigma. So sigma is equal to 1 by rho. Its unit will be mho per meter. Dimension formula m minus 1 L minus 3 T cube A square. So conductivity is inverse of resistivity. So sigma we can write it as n E square tau divided by m. Since rho we got it as m by n E square tau. So here it is reciprocal. So immediately we can invert. Depends on relaxation time n and tau. Conductance. It is the reciprocal of resistance. Reciprocal of resistance is called conductance. K is equal to 1 by R. Unit will be 1 by ohm, ohm inverse or Siemens. So K also can be written as n E square tau by m into L by A. Reciprocal of resistance is called conductance. Reciprocal of resistivity is called conductivity. Next, stretching of a wire. If a conducting wire stretches, its length increases, area of cross section decreases. So, resistance increases but volume remains constant. Suppose, for a conducting wire before stretching, its length is L1. Area of cross section let us call A1. Radius we can consider as R1. Diameter as D1. Then R will be, or resistance R1 will be rho L1 by A1. After stretching, its length becomes A2. Area of cross section A2. Radius will become R2. Diameter D2. Resistance R2 will be equal to rho L2 by A2. Ratio of resistance before and after stretching we can directly write in terms of length, in terms of area of cross section, in terms of radius or diameter. If length is given, then R is proportional to L square. Radius is given, R is inversely proportional to L square. R to the power 4. Let us see, because volume is constant. If a conducting wire stretches, its length increases, area of cross section decreases. So resistance increases, but volume of the wire remains same. For a conducting wire, before stretching, length is L1, area of cross section R1, radius is R1, A1 is area of cross section, diameter D1. Then R1 will be equal to rho L1 by A1. Similarly, after stretching, length is L2, area of cross section A2, radius R2, diameter D2. Then R2 will be equal to rho L2 by A2. Ratio of resistances before and after stretching. R1 by R2 is equal to L1 by L2 into A2 by A1. That is equal to L1 by L2 square. That is equal to A2 by A1 square. That is equal to R2 by R1 to the power 4. Or in terms of diameter, D2 by D1 to the power 4. If length is given, then R proportional to L square. R1 by R2 is equal to L1 by L2 whole square. If radius is given, then R inversely proportional to R to the power 4. So R1 by R2 is equal to R2 by R1 radius to the power 4. So volume of the matter remains same, only length will increase, area of cross section is going to decrease. Electrical conducting material for specific use. Suppose first one I take filament of electric bulb. Generally it is made up of material tungsten, which has high resistivity and high melting point. Second, element of heater. We have such as heater, geyser or iron box, press, etc. It is made up of nichrome wire, which has high resistivity and high melting point. Resistances of a resistance box. They are made up of alloy, manganese, constant or nichrome. These materials have moderate resistivity, which is practically independent of temperature, so that the specific value of resistance does not alter with minor change in temperature, which is practically independent of temperature. Fuse wire. It is made up of tin, lead, alloy, 63% tin plus 37% lead. It has low melting point and high resistivity. It is used in series as a safety device in an electrical circuit and is designed so as to melt and thereby open the circuit if the current exceeds a predetermined value due to some fault. The function of fuse is independent of its length. Safe current of fuse wire relates with the radius as I is proportional to 3 by 2. Safe current of fuse wire depends on radius, I proportional to R to the power 3 by 2. R is radius. Thermistors. A thermistor is a heat sensitive resistor usually prepared from oxides of various metals such as nickel, copper, cobalt, iron, etc. These compounds are also called semiconductor. For thermistor, alpha is very high, which may be positive or negative. Resistance of thermistors changes very rapidly with the change of temperature. Thermistors are used to detect small temperature changes and to measure very low temperature. A thermistor is a heat sensitive resistor, usually prepared from oxides of various metals such as nickel, copper, cobalt, iron, etc. These compounds are also called semiconductor. For thermistors, alpha is very high, which may be positive or negative. The resistance of thermistor changes very rapidly with change of temperature. Thermistors are used to detect small temperature change and to measure very low temperature. Color coding of resistance. These are the resistance shown in the figure. They have some color coding on this. To know the value of resistance, color codes are used. These codes are printed in the form of sets of rings or strips as shown here. By reading the value of color bands, we can estimate the value of resistances. A carbon resistance has normally 4 colored rings, say bands, as A band, B, C and D as shown in the figure. Color band A and B indicates first 2 significant digits of resistance in ohms. C indicates decimal multiplier, the number of zeros that follows the 2 significant figures A and B. And band D indicates the tolerance in percentage about the indicated value, or in other words, it represents the percentage accuracy of the indicated values. The tolerance in the case of gold is plus or minus 5%, in case of silver plus or minus 10%. If only 3 bands are marked on the carbon resistance, then it indicates tolerance is 20%. That means this 4th band is missing. To know the value of resistance, color code is used. These codes are printed in form of set of rings or strips by reading the values of color bands. We can estimate the value of resistance. The carbon resistance are normally 4 colored rings or bands A, B, C, D as shown in the figure. Color band A and B indicates first 2 significant figures of resistance in ohms. Band C indicates the decimal multiplier, that is the number of zeros that follows the 2 significant figures A and B. Band D indicates the tolerance in percentage, or it represents percentage accuracy of the indicated value. Gold plus or minus 5%, silver plus or minus 10%, no band or no color plus or minus 20%. This indicates tolerance. That means there is no color on the 4th band, then it is plus or minus 20%. Color code for carbon resistance. So depending on the color codes A and B and multiplier C is decided. First color we will take it as black. A and B multipliers of the significant digit is 0 and multiplier is 10 to the power 0 for C. Next we will take brown. A and B significant number 1. Multiplier 10 to the power 1. Next comes red. A and B is 2. 10 to the power 2. Next orange. A and B is 3. This is 10 to the power 3. Then comes yellow. 4. 10 to the power 4. Next is green. A and B is 5. 10 to the power 5. Then blue. 6. 10 to the power 6. Then violet. 7. 10 to the power 7. Then comes grey. 8. 10 to the power 8. And lastly white. 9. 10 to the power 9. So to remember these color codes A and B multiplier, there is an easy method of doing it. First letter as an aid to memory. This is B. Brown B. Red R. Orange O. Yellow Y. Green G. Blue is B. V is violet. Gray is again G. And white W. To remember the sequence of the color code, following sentence should be kept in memory. B.B. Roy of Great Britain has very good wife. To remember the sequence of color code, the following sentence should be kept in memory. B.B. Roy of Great Britain has very good wife. B.B. Roy of Great Britain has very good wife. Black, brown, red, orange, yellow, green, blue, violet, grey and white.